All right, today we're going to talk about compositions of functions and decomposing functions. Another way to combine functions is to use the output of one function as the input of another. This operation is called composite of functions, and we did this in Math 3 as well. If f and g are functions, then the composite function of f and g is, and we have f of g of x. Notice that this is using an open circle. So there's two different notations. You can write it with the open circle or you can write it with the parentheses. So these notations are the same. So this would be read f of g of x, or the other one would be read g of f of x. So sometimes we say f followed by, g followed by f, or f of g of x is the same kind of notation. Be sure to note the symbol does not represent the product of f times g. So keep in mind that these are not equal. We're not multiplying the functions. We are doing a composition of functions. We're composing one function with the other. So in order to do compositions, you would have to be given what the functions are. So for this first example, it gives us f of x and g of x, and it says find each of the following. And let's actually go ahead and put this in a different color. So the first one we have is g of f of -2, which you can also write with the parenthesis notation. So you always want to evaluate the inner function first and then the outer function. So our inner function in this case is f of -2. So we're going to evaluate that first. And when I plug -2 into my function for x for the f function, we end up with -8. So then we're going to take this answer and plug it into the outer function, which is g. So g of -8 goes into our g of x function, so -8 squared, which is 64. So that would be the entire answer of our composition. Looking at the next one, now we have f of g of 4. So those are the two different notations. So now we're evaluating first g of 4. So that would be 4 squared, which is 16. And then we take that answer and plug it into f. So f of 16 gives us 3 times 16 minus 2, which ends up giving us 46. And we do the same thing for the next one, except for now, notice that we're not just plugging in numbers, we're plugging a function into the other function. So now we're plugging g of x into f. So we have f of, and g of x is, again, x squared. So everywhere we have an x in the f function, we're going to plug in x squared. Sometimes it helps if you use different colors when you're doing this. So that would be our g of x function plugged into x for f of x. So this gives us 3x squared minus 2 when we simplify. Remember, when you're simplifying, no parentheses, combine like terms. The next one we have is we're switching the order. So g of f of x. So now we're plugging in f into the g function. So we have g of, and we're plugging in 3x minus 2. So everywhere we have an x, we're going to be plugging in that 3x minus 2 into our function. So if we have a quantity squared because it has a minus sign right there, we have to FOIL. Remember, we can't just use the properties of exponents. It only works for multiplication and division. So when we FOIL this out, 3x times 3x gives us 9x squared. And then that would be minus 6x, we just did those two, and then minus 6x plus 4, and then combine your like terms. So 9x squared minus 12x plus 4. So you always want to FOIL out because otherwise you would miss those middle terms. The next one we have is g of x. So we're plugging our g of x function into itself. So g of x is just, again, x squared. So we would get x squared, and there's no addition or subtraction between the terms, so we can use our properties or rules of exponents. So this would be x to the 4th power. So that is just a reminder of what we did in Math 3, and now we're going to take it a step further and find the domain of the composition of functions. So in the diagram to the right, the output for g of x is used as the input at f. The domain of f of g is a set of all real numbers such that x is in the domain of g, g of x is in the domain of f. So what does that mean? So in other words, I wrote it down here. So we're going to find the domain of g of x, what we substitute in if we're doing this function, and then we're going to look to see if it's in the domain of the composition answer. If we're doing g of f of x, we're going to find the domain of f of x, what we substitute in, and then look to see if it's in the domain of the composition. So let's go ahead and do some examples. So for the first one, we have the square root of x minus 2, and g of x is x squared minus 1. So the first thing we're going to do is our composition. So we have h of x equals f of g of x. And again, if you want to use the other notation, f parentheses g parentheses x. So our inner function is g of x. So we're plugging that into f. So we're doing f of g of x, which is x squared minus 1. And so that gives us the square root. And everywhere we have an x, we're going to replace that with x squared minus 1. And then we just have to simplify. So we can drop the parentheses here. Minus 1 minus 2 gives us minus 3. So this gives us the square root of x squared minus 3. So this would be our answer for the composition. So if we want to find the domain, we have to look at the domain of what we substituted in. So what did we substitute in? We substituted in g of x. So we want to find g of x's domain. The domain of g of x would be, and so if we make our number line, remember we look for our red flags. There's no variables in the denominator. There are no variables underneath even roots. So that means the domain is all real numbers for g of x. So then we look at the domain of our composition answer. So I'm just going to write D of C for composition. So the domain of the composition, we do have a radical with variables underneath, so we have to take what's underneath the radical and set it equal to 0 since it's in the numerator. So then we get x squared equals 3. So then x equals plus or minus the square root of 3, because remember we have to do plus or minus your answer when you take the square root. So then on our number line, we would have negative 3 and 3, because it's in the numerator, we can have closed circles, because if we plug those values in, it would just give us a square root of 0, which is 0. And then remember, we do our test values to the left of negative 3, in between negative 3 and 3, and above 3. So a test value below negative 3 would be negative 4. If I plug that into my composition answer, I get negative 4 squared, which is 16 minus 3. And notice that that's going to give us a real number answer. So that means that numbers below negative 3 are going to work. In between negative 3 is a number such as 0. If I plug 0 into my equation, I get 0 squared minus 3, which is the square root of negative 3, which is imaginary. So those are not included in our solution answer for the domain. And then values above, oh, and you know what? I just realized I didn't put the square root there. I'm using 3, so I need to do that again. This is the square root of 3. Negative root 3 and root 3. So we did a number below negative root 3 already, but and also in between would be 0 still. So above root 3, again, we could do any number above root 3. So let's do 3. So if I plug in 3, 3 squared is 9. 9 minus 3 also give me real number answers. So those values are going to work. And like I said before, when you plug in negative root 3 or positive root 3, it gives you 0, which is why we have closed circles there. So when you're doing the domain of the entire composition, you look at where those two overlap. So they overlap from negative infinity to negative root 3, and then they don't overlap in between, and then from root 3 to infinity. So that means that the domain would be negative infinity to negative root 3, bracket, union, bracket, root 3 to infinity. Looking at the next one, we're going to do the same thing, except for we're switching the order of the composition. We're doing g of f of x and seeing how that changes our answer. So now if I do g of f of x, g is the outside function. And we're plugging in f of x, which is the square root of x minus 2. And g of x is x squared minus 1. So we're plugging in the square root of x minus 2 in for x. And when we simplify, when you have a square root of something squared, that cancels out the square root. So that becomes x minus 2 minus 1, which gives us x minus 3. So again, now what we're substituting in is f of x. So we have to look at the domain of f of x. So f of x, if you go back up here, we have the square root of x minus 2. Because it's a square root with variables underneath and it's in the numerator, we can set it equal to 0 to solve. So when we solve this, we get x equals 2. So on my number line, I have 2, and it's a closed circle because I can be equal to 2 because I would get the square root of 0. And then I'm going to do my test values. Below 2 would be 0. So if I plug 0 into my function, I get the square root of 0 minus 2, which is the square root of negative 2, which is imaginary, so we don't shade that side of our number line. If I plug in 3, 3 minus 2 is 1, and the square root of 1 is 1, which is a real number. So anything above 2 is going to give us real number answers. Then we want to look at the domain of our composition. Our composition here, notice that is x plus 3, which does not have any restrictions on the variables. So that would mean that would look like it's all real numbers for our answer. But this is why you always want to look at the domain of what you're substituting into your equation and then the domain of the answer, because in this case that it appears the radical disappears, but it's still part of your original problem. You still have to plug in a radical to get your answer. And so that means that our domain for the entire composition would be where they overlap. So they overlap from 2 to infinity. So brackets 2 to infinity. So that would be our domain. So again, you have to be very careful about looking at the domain of what you substitute in. How does it overlap with the composition? And then wherever that overlap is going to give you the entire domain. Okay, so I changed these for the next one, which should be correct on your paper. So we're using f of x as 1 over x plus 3 and g of x just as x squared. So let's go ahead and find the compositions and their domain. So first we're doing f of g of x. So the inner function is g of x. So we have f of g of x, which it would be f parentheses. We're doing 1 over parentheses plus 3. G of x we're using as x squared. So that gives us 1 over x squared plus 3 for the composition answer. Now let's look at the domain. So we have to look at the domain of what we're substituting in, which is g of x. So the domain of g of x is quadratic. So there's no variables in the denominator or underneath an even root. So it's all real numbers. And the domain of the composition, notice that we do have variable in the denominator. So whatever is in the denominator cannot be equal to 0. So you can set that not equal to 0 and solve. So we get x squared is not equal to negative 3. So x cannot be equal to plus or minus the square root of negative 3, which means x cannot be equal to plus or minus I root 3. So notice that gives us imaginary answers. And we've talked about this before. That means whatever you plug in for x here is never going to make your denominator 0. If you plug in 0, you get 0 squared plus 3. If you plug in a negative value, you're squaring it and then again adding 3 to it. So that means the domain is still all real numbers. So the domain for the entire composition here would be negative infinity to infinity. So let's go ahead and look at the next compositions. Now we're doing g of f of x, or you can write that as g parenthesis f parenthesis x. So the inside function is now f of x. We have g parentheses. So we have parentheses squared because it's x squared, and we're plugging in f of x, which is the square root of x. Or no, sorry, not the square root of x. We're doing the, sorry, I forgot we changed that, the 1 over x plus 3. Okay. So for this, that means then if we simplify, we get 1 squared in the numerator, which is just 1 over x plus 3 squared in the denominator. So then if we FOIL that out to simplify, it means no parentheses, we would have x plus 3 times x plus 3, which gives us x squared plus 3x plus 3x plus 9. So when we combine like terms, x squared plus 6x plus 9. So that gives me my composition answer. And now we need to find the domain. So we need to look at the domain of what we're substituting in, which is f of x. Remember, we're using this function over here. So the domain of f of x, we know that what makes my denominator 0 is -3. So on my number line, I have -3 with an open circle because we cannot be equal to those values that make our denominator 0. And remember, there's no radical to worry about. So no matter what we plug in, we're not going to get imaginary answers because there's no even root. And so we're only concerned with -3 because that makes our denominator 0 and we can't divide by 0. So that means every other number that we pick is going to work, which we've talked about before when we did our domain notes. And so then now we're going to look at the domain of our composition and see where the two overlap. So for composition now, you'll notice that we have x squared plus 6x plus 9 in denominator, so we know that cannot be equal to 0. And so for this one, you get the same thing. We already know that factors into x plus 3 squared cannot be equal to 0. So when you take the square of 0, it's just 0. So x plus 3 is not equal to 0. So x not equal to -3. So we get the same thing with an open circle, and every other number that we plug in is going to work besides the -3. And so that means then the domain for the entire composition is -infinity to -3, parenthesis, union, parenthesis, -3 to infinity. I'm running out of room here. There we go. All right, so that's finding the compositions and their domain. Next, we're going to look at decomposing functions. So when you decompose a composite function, you're finding the components of the composition. You're looking for an inner function and an outer function. So for example, it says, for each function h, find the functions f and g such that h of x equals f of g of x. So notice that we're using h of x for the composition. The inside function is g of x, and the outside function is f of x. So what could we use for our inside function? So notice that we have x plus 3 here, so we could use x plus 3. So if g of x was x plus 3, then the outside function would have to be x squared. So we're saying g of x equals x plus 3 and f of x equals x squared. And then you can check your work. So if we do f of g of x, it should equal h of x. So this is f of g of x is x plus 3. And we're plugging that in for x. So when we plug that in, we get x plus 3 quantities squared, which was equal to h of x. So that shows that that works. So same thing for the next one. So if we use g of x as x minus 5, then f of x would have to be 1 over x. And again, if you wanted to check your work, f of g of x would be equal to f of g of x, which is x minus 5. So 1 over x minus 5, because you're plugging in g of x for x into the f function, which equals h of x. So see if you can do the next two on your own, and then when you're done, on pause to check your work. For this one, if you use x plus 2, then f of x would be equal to the square root of x. For this one, you would use g of x as x minus 2, and then f of x would be equal to x squared minus 4x plus 5. And then again, you could always check your work by doing the actual composition. So it says, write h as a composition for the next example of two functions in two different ways. So we're going to see if we can do this in multiple ways. So we have to make up our own composition. So I'm going to write it over here. So we're going to do h of x equals g of f of x. So the inner function is f of x. So one way we can do this would be if f of x was equal to x cubed minus 5, then think about what would g of x have to be equal to. So g of x would then have to be the square root of x, because if we plug this into x here, we would get h of x. So let's try to do another one. What if we did f of x is equal to x cubed? Then what would g of x have to be equal to? G of x would be equal to the square root of x minus 5. So now if you plug in x cubed into x, you get h of x out. And you can make it anything that you want, as long as when you plug it in and do the composition, it gives you your answer. So like, for example, what if I did f of x was equal to 1 over x? What would g of x have to be equal to? So if I did that, then g of x would have to be x to the 4th minus 5. And so just to show you, if I did the composition, g of f of x, so we're doing g of 1 over x into the square root of something to the 4th. We can see that's not going to work. So if we did, sorry, just go ahead and go back here. So if this was negative 3, so then we would get 1 over x to the negative 3 minus 5. And so that means we would get the square root of 1 to the negative 3, which means it goes to the denominator, over x to the negative 3 minus 5. So that would give us x cubed over 1 cubed, which is just x cubed minus 5. So notice that that one would work out. So then how about you pause the video, do the next one on your own when you're done, on pause, and check your work. So I'm going to do, again, h of x equals g of f of x like the last one. So we need two functions, f of x. So if f of x is equal to 3x squared plus 1, then g of x would be equal to the square root of x. And then we could do f of x is equal to maybe just 3x squared. Then g of x would be equal to the square root of x plus 1. You could also do, let's say you had f of x as just x, or you could do x squared. So you could do x or x squared. So let's do x squared. Then g of x would have to be equal to the square root of 3x plus 1. So there's lots of different answer combinations that you could have. All right, the next example, say, use the graphs of f and g to evaluate the functions. So looks like this top graph is f of x, and the bottom graph is g of x. So I'm going to just highlight all the f's here. All right, and then so we can do g of x. Okay, just helps me to use different colors. So the inside function here, remember if we rewrite this, would be f of g of 3. So that means we're evaluating g of 3 first. So we're going to look at the graph of g of x. When the x value is 3, our y value is 1. And then that means the next part would be to do f of 1. So when our x value is 1, our y value is equal to 2. So that would be our answer for the composition. For the next one, we have, and you can rewrite this as f open circle g of 1. That would be the other notation. So g of 1 is the inside function. So when we go to our g of x function, look at an x value of 1, the y value is 3. So then we want to do f of 3. So when we do f of 3, we get 2. For the next one, we have f of g of 4. So g of 4 is the first one that we want to do. So looking at the g of x graph, when we have an x value of 4, our y value is 0. And then f of 0, so an x value of 0 gives us a y value of 4. And then over here we have f of 1. So on the f graph of 1, we get 2. And then our outer function is g. So g of 2, when x value is 2, our y value is 2. And then notice we're multiplying these functions because we have a multiplication symbol here. So 4 times 2 gives us, oops, I wrote 8. 4 times 2 is 8. So that would be the answer for our composition. The next one we're dividing. So f of negative 1 on the graph means when I have an x value of negative 1, my y value is 6. For f of x, g of 3 is 1 on the graph, and then f of an x value of 1 gives us 2. So 6 divided by 2 is 3. So then pause the video, do these next ones on your own. When you're done, you can unpause to check your work. So g of 4 on the g of x graph gives us 0, and then f of 0 gives us 4, because that would be right here in my graph. 4, and then f of 2 is 0, and g of 0 is 4. All right, so that's from the graphs. And then we have our application. The weekly cost of producing X units in a manufacturing process is given by the function C of X equals 48X plus 1,150. The number of units in T hours is given by X of T equals 40T. Find and interpret C of X of T. So we're plugging in X of T into the cost function. So we have, this would be equal to C parenthesis X parenthesis T if it helps you to write the other notation. So we have C of something equals 48 something plus 1150. And that something is our X of T function, which is 40T. So then we're just going to simplify, multiply 48 times 40. So we get this is equal to 1,920 T plus 1150. So that ends up giving us C of T. So what does this mean? This gives us the cost given per the number of hours. Because we're using the cost per time now. So then how many hours would need to pass for the cost to be 3,070? So we're plugging 3,070 into C of T to our composition that we did and solving. So subtract 1,150 gives you 1920 equals 1920 T. So then T is equal to 1, so 1 hour. So after 1 hour, the cost would be $3,000 $3,070. And that is it for our composition of functions and finding the domain and decomposing, and again, some applications.